All right, so in this opening exercise, it says when an earthquake hits, the ground shifts abruptly due to forces created when the tectonic plates along fault lines rub together. As the tectonic plates shift and move, the intense shaking can even cause the physical movement of objects as large as buildings. Completely true, by the way, guys. Suppose an earthquake causes all these points in a town to shift 10 feet to the north and 5 feet to the east. Using this model right here, explain how the diagram shown above could be said to represent the shifting caused by an earthquake. So meaning, how would you write this out? Going from this coordinate to this coordinate. Okay, let's take our brains away from systems for right now. No need to do an equation, just a simple sentence.
10 feet up and
All right, let's use if this is north, east, southwest. Same concept, get a little more specific. That's it. So explain how the diagram above can be said representing the shift of the, where's my, oh, I got to turn it on. So again, this right here would be, you said 10 feet north. So it shifts 10 feet north and what? 5 feet east. All right. It's all right. It's all right. But you had the right idea on how to describe the transformation. Questions on that? Basically just rephrasing what was told at the beginning of this directions. Part B, I'm not going to move it, but draw another arrow that shows the same shift and explain how you drew your answer. So how would you randomly draw another vector here? Yeah, just same. Just draw a random point anywhere you want. Now, how do I know where this vector goes? How do I get there? That's it. So I'm going to go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Roughly. Oh, yeah, it's fine. All right. But it's a rough estimate, right? And how did you just do that? By counting, right? Or looking at that one and using that to be able to count. So in part B, this is the answer for part B. Again, you would just shift a coordinate 5 numbers to the right or east. Well, that was in a situational. Now we're trying to describe how we would do it. And 10 numbers up. Questions so far? So if I have a translation of 5 to the east, 10 to the north, I can apply it to any coordinate in space for the situation. Right? And they have a whole bunch of different situations, right? Are all of these vectors the exact same? Yeah, they have the same direction and the same distance, right? So their magnitude is the same. Therefore, they're all the same vectors, just moving different points in time to a different part of the plane. All right. So let's get into this next part of the review. So in exercise 1 through 3, we have several vectors here drawn. All of these are drawn on your paper, so you don't got to worry about looking up there. So I'm going to go a little bit further. My question to you is, which arrows represent the same vectors? Take about 2 minutes to write those down. Group up all the vectors that are the same. We'll check these here in a second. right, does everyone have their answers? All right, there we go. So what vectors are the same? Give me one group. All right, good. A, U, and W. Give me another group. C and D. Give me one more group. V and B. How do you know that these are all the same vectors? Okay. What else do you need to be paying? Okay, well, let me answer this question here. Why do C and U not represent the same vectors? I heard it. The direction is different. They have the same distance, but the direction is different. So we don't need to just look at the same distance of it, but you got to pay attention to the arrows as well. For it to be the exact vector, the direction and the magnitude or the distance of the vector has to be the same. So therefore, this right here, they are opposite of each other, I guess you could say. Right. Questions on that? So main thing to pay attention to in vectors. Same direction, same distance, they're the same. They're just in different parts of space. If they are the same distance but different directions, they are not the same. They tell a point to go in a different direction. Any questions? Pretty straightforward still. And just visually looking at vectors. Let's carry this on to the next question then. In question 3, it says, after the first earthquake shifted points 5 feet east and 10 feet north, suppose a second earthquake hits the town and all the points shift 6 feet east and 9 feet south. We're going to write and draw a vector. We're going to call it T that represents this shift caused by the second earthquake. So here's my original building landmark, whatever you want to call it. It shifted 5 feet east, 10 feet north. How would I now illustrate a 6 feet east and a 9 feet south? Where do I start? Let's go with that one. Where do I start? Not quite. You start at the tip. If you recall from vectors, when we are adding vectors together, we go from tip to tail, right? So the tail of the new vector starts from the tip of the old vector. So that means my new origin spot would be at the tip of V. So going from here, how do I now go to my new tip for the new vector? Okay, so from here, I'm going to go 1, 2, so going by ones. Okay, 1, 2, 3, 4, 5, 6. And then down. Why would I go down? South, right? Very good. So that'd be here, I think, right? So again, I start from the tip. This is where the tail of my new vector is. And then the tip will end of this one. They want us to call this T. So any questions on how I just drew T? So again, big thing to remember, start from the tip when you are adding a vector to it. All right, part B says, which earthquake then, the first or the second, shifted points in the town the furthest? And then how would you know this? How would I figure out which one's furthest? Go ahead. Very good. These are basically triangles, right? We started with the Pythagorean theorem. A squared plus B squared equals C squared. It's usually the one thing in life y'all remember, just don't know how it's applied. But these are all little triangles, right? If you recall, when we used this Pythagorean theorem to find the distance, what did our overall equation always ended up being? If I wanted to know the distance of any one of these vectors, we came up with an overall equation that always worked. What was it? There it was. We determined that we were always just doing the square root of a squared plus b squared, right? This gave us the distance, which was known as our magnitude. Oh, perfect. How'd you do? Yeah. All right. I'll grade it and then I'll put it in after this. So with this, go ahead. Yes, because what you're solving for is this side here. So you would have to take the square root of these results to get our C, which is that diagonal of our triangle, our hypotenuse. Go ahead. Remember our notation from module 1, double bracket absolute means magnitude. It's notation purposes. So this means magnitude. And magnitude tells us two things, distance and direction. Yes, you're right. But this was just notation purposes. So we're bringing this back in as a review for right now. So to figure out which one moved a point the furthest, we got to go find the magnitude of both V and T. Do that now. I'll give you about a minute to determine which one moved their stuff furthest. Don't necessarily have to have a calculator. You can actually just kind of look at the inside radical number and kind of assume which one is bigger or smaller. Say one more time. If you can just do it in your head, that's fine. Yeah, this is your notes. So however you want your future Avery to see how you do it. How past Avery did it, I guess. Go ahead. All right, so let's look at V for now to make sure you have it right, and I'll give you some more time on T. How would I figure out the distance for V? Good, 5 squared plus 10 squared. So that right there would give me 25 plus 100, which is the square root of 125. Again, you don't need to go find a decimal version. You just keep it like this if you'd like, because when you're comparing two things, you don't necessarily need the decimal. You can just go, it's 125 smaller or bigger than the other inside radicand. Go ahead. This is your A. This is your B.
Well, I thought we were so.
You're doing both. You're comparing to see which one's bigger. They are.
Oh, we're doing both.
To figure out which one's bigger. You're good. So go ahead and finish up V. I'll give you some more time. Not V, sorry, T. Yes, visually you can as well. But not always will the vectors be graphed. Maybe it'll just be a straight up answer. Hey, which vector has a bigger magnitude? And then you could just quickly do the math without having to graph it too. But you could necessarily just graph it and compare. All right, so for our T, what numbers do I plug in this time? Very good. So that will give you 36 plus 81, which gives me what? So again, without actually typing this into our calculator to figure out what the decimal version, which one's bigger? The 125. So that means my vector V moved or shift the town further. Questions on how to analyze that question? All right. All right, so let's look at the next example and let's put some more of that symboling back into our brain from module 1. So the magnitude of a vector is typically capital, or not capital, bolded V. It's kind of hard to do that with, you're on paper, you're coloring it really good. Is written also as the inequality looking symbols. This indicates that this is a vector versus when it's in this form, this is just a coordinate. So this would just be a point in space versus this is more like a ray in space. And then we, again, to help us with this magnitude, we bring this double absolute value with the vector in there to show the reader, hey, I'm looking at distance and direction right now. Again, we're going to use this language of translations to help us answer a lot of these questions about our vectors and how it's changing vertically and horizontally. So on part A, it says simply find the magnitude of these two situations and explain your answer. We actually already did this. I don't know why it's asking us to do it again, but we'll put the notation. So the magnitude of V gave us what? Square root of 125. And the magnitude of T gave me, all right, we're just now throwing in that notation point of view. Maybe I got a little ahead of myself in the last exercise. So therefore, also, we can then write out our general formula. To find any magnitude, I simply just need to do the square root of a squared plus b squared. Okay. Again, a lot of this stuff should look familiar. We did this in module 1. Any questions? Okay. We also learned how to add, subtract, and multiply vectors. So let's kind of review our adding, and then that will kind of probably give us a good stopping point, and then we'll bring in multiplication on Monday as a review. So given that b, or the vector v, is equal to 3, 7, and t is equal to negative 5, 2, how would I figure out b plus t? Add what specifically? Very good. You want to add the x values, or you could also say the horizontal movement, and then add it to your vertical movement. And that was simply all you had to do. And that's it. Told you I like this a little bit better. So to figure out what v plus t is, I would simply, again, just do 3 plus negative 5, comma 7 plus 2. No, you don't have to write this out. I'm just showing you what you're doing. So 3 plus negative 5 is negative 2, and 7 plus 2 is 9. I'm good with that straight up as the answer if you know that that's what you're adding. All right, then part B just simply says, now draw a diagram that represents this addition and show the resulting sum of the two vectors. So y'all don't have a graph on y'all's, right? So let's do this real quick. We'll do a little drawing. So to first start this off, if I'm doing b plus t, just like what we did first, I need to graph b first. So that would be 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. So roughly, this would be my V. Now I'm going to graph T from the tip of V. So again, this means I'm going to go left, 1, 2, 3, 4, 5. And then what was it? Up 2 more. So there's my T. And what coordinate did that just land on? Negative 2, 9. So there's your V plus T right there. There you go. And that's a great stopping point. We'll talk about scalar multiplication and subtraction on Monday. We're good?